Okay, so what we're gonna do is we're gonna prove Proposition 47, Book 1 of Elements, Euclid's Elements. So it says, in right-angled triangles, so this is any right triangle, the square on the hypotenuse, and what he means is the area of the square. So you might want to add some detail because he just says the square, but he's referring to the area of the square on the hypotenuse. And the hypotenuse, we should see, is the side of the triangle opposite the right angle. So what is the hypotenuse? You have a right triangle. The hypotenuse is this side right here. And the square on that hypotenuse just looks to be if you were to draw a square onto that like this, of where this is obviously the same, all four sides the same, and it's a square on the hypotenuse. So he's saying the area of the square on the hypotenuse is equal to the sum of the squares on the other two sides, or the sides where the sides are this side and this side. So this side, the area of this square plus the area of this square is equal to the area of this square. Now let's get to the proof. So the first thing I'm going to do is I'm going to draw any right triangle. So let triangle ABC be a right-angled triangle. So here it is, triangle ABC. And we could say with angle A right angle. Now what I'm going to say is I'm going to make this statement clear what we exactly want to show. So we should see that this square BCE, right? BCE DB, right? If we go all the way around. So square BCED is the square on the hypotenuse. So I'm going to write that BCED, right? And when I put it in brackets, I mean the area of must be equal to the area of the square on the squares on the sides. So I got, then the next thing, I'm going to call this A, B, F, G, plus the other square on the other side, A, C, K, H. And again, when I put it in brackets, it just means the area of. So we want to show this relationship. We want to show this right here. Now, to show this, what I'm going to say is I'm going to give you the overall idea. I'm going to show that rectangle right here, this rectangle, MCEL, is equal to the area of this square. And that rectangle BMLD is equal to the area of this square. And then we should see that it's clear that this area, the area of this rectangle, plus the area of this rectangle is clearly the area of the entire square BCED. So if I show that this rectangle is the same as this square, right? And then this rectangle has the same area as this square, then that means that this square plus this square is equal to this whole square. Now, to start to show that, right, we want to just write the relationship that we can firstly see that's obvious. So the first relationship we see is that first one that I said, where rectangle or square BCED is equal to, right, the sum of these two rectangles, MCEL plus BMLD. And now I want to show, right, if I'm able to show that this right? MCLD is this square, ACHK, then, this one would be this one. And then I'm going to show that this one is this one, right? And then I'm done. So now I just have to work on showing, we need to show that ABFG is equal to BM, I did this a little off, but it's fine, BMLD, and I need to show that ACKH is equal to MCEL. And once I show these two, then I'm done, right? So to show this equality and this equality, to show this, right? To show this, okay, we're gonna prove that triangle. So it doesn't seem like it's useful what we're doing right now, but it all comes together. So why do I care about this triangle? So I want this triangle BKC is going to be congruent to triangle AEC. We show this first. Okay? How? Why is this true? Well, if we look at our picture, right, BC is the same thing as CE. So BC is congruent to CE. Because this side of the square must be the same as this side of the square. So the two triangles I'm looking at right now, right, are AEC. So if we look at that, let's get a good idea of what we're AEC, right? This is A up here, right? This point is here, and then C is here. So that's one triangle I'm looking at. The other triangle is here, BKC. So BKC looks like this. When I pull it out a little bit, BCK, or BKC. And again, I should see that my first statement is BC is the same thing as CE. So these two are the same. Then, if we look, AC, or wait, where is it? Oh, wait. Yeah, AC, this side, in this triangle, right? AC is the same thing as CK. Because, again, this is two sides of a square. So AC is the same thing as CK. And now, if I could show that this angle here is the same as this one, then by side angle side, these two triangles are indeed congruent. So I have now that this angle here, whatever you want to call it, let's call it dot, we should see that this is 90 degrees plus dot, and that's this angle, BCK, right here, BCK. That's, again, 90 degrees plus dot. And then if we look at this angle, ACE, right here, it's also 90 degrees plus dot. It's this angle, right? It's this angle. From here to here, it's the 90 degrees plus dot right here. So we can say, and angle ACE is congruent to angle BCK, since they are both the sum of an angle and 90 degrees. The sum of an angle and a right angle. Okay. So then we can say then by side angle side, we have that the triangles are congruent. What we wanted, BKC, is congruent to triangle AEC. Now once we have that, we should then conclude that, of course, if they're congruent, their areas are equal. So triangle, so yeah, BKC, that's referring to the area of triangle BKC, has to be equal to the area of AEC. Clearly, if they're the same triangle and they overlap, then the amount of space that they have on the inside is going to be the same. Okay, now once we have this relationship, we begin to look at the relationships between the area of BKC, and BKC is going to be, which one? It's going to be, it's going to be the area of this square. So we need to show that the area of BKC times 2 is the area of this square. So what we can say is we can say that if we look at this triangle BKC right here, right? And we say to ourselves, okay, if CK is a base, right? Then what's the height? Well, the height then goes from B, because that's the angle that's opposite this side or corresponding with this side. Or that's the point that's corresponding with side CK. And if you look, the altitude looks something like this. And if you extend CK, the altitude looks something like this. Or the height times CK is the area of this triangle. So the area of BKC is equal to CK times a height divided by 2. And the height, this is H, we should see is equal to the distance between H and K. This is a right angle. And we can prove, if we took our time, using a different bunch of theorems, we could prove that H is the same length as HK. And this is what Euclid did in a previous proposition. So we can say, since H equals capital HK, the height, right? We have this relation. We have BKC is equal to CK times HK divided by 2. And then if we look at CK times HK, we should see that CK is here, right? This is CK times HK is the area of this square. So then I'm going to say, when I multiply by 2, I'm going to get 2 times BKC is equal to, when I multiply by 2 over here, this 2 cancels, is CK times HK, but we can clearly see that CK times HK is the area of that square, so I have ACKH is the way I typically been writing it. 2 times the area of BKC is equal to the area of ACKH. Now, we can do this, we can play a similar game, but now we want to look at the relationship between this triangle, and this rectangle. So if we look, right, they share that CE side, the triangle and the rectangle. So it's likely that it has something to do with that. So let's look. Let's write more. Let's write up here. So I'm gonna say that what am I looking for? I'm looking for something involving AEC. So AEC, if we look, is CE times what height? And it would be drawn from A, that height, down as so. And then this is a 90-degree angle. And similarly, if we call it H, this length is the same thing as LE. So we're going to say that this is h times, right, the area of this is h times CE by 2. And then this would imply that since h, we just by the same logic, h is the same length as LE, we can write this as LE times CE by 2. And then you multiply by 2 to get 2 times AEC is equal to LE times CE. But again, we should see LE, this length, times this length is the area of this rectangle. So now we have another relationship. So let's label some of our relationships. Let's call this one star. And then now we're going to get another relationship. Let's go over here. We're going to say that 2 times AEC is equal to MCEL. And, well, let's see. We got another star. I don't know which. And then, okay, so now what we can say is well, let's see what we got. We got that, okay, B, the area of the two triangles are the same, right? So then if I take this relationship and I multiply it by 2, I'm going to get, and what we could do, let's call this triple star, this relationship, right? If I combine star, double star, and triple star, I'm going to get the relationship I need because 2 times BKC is going to be equal to 2 times AEC. And then 2 times AEC is MCEL. And then 2 times BKC is going to be, where is it? 2 times BKC is equal to ACKH. And now I've shown that the area of this rectangle is the area of this square. So now, right, now we have that. Let's go, let's try and get this all on one page. Let's see if this can be done. Okay. Let's go like that. Let's see. Okay, so now, right, pulling from here, this is our key. This is a key relationship that we wound up with. We can say by a symmetric argument. So what we should see is that I could, right, erase a lot here and draw in a few interesting lines as well to get the fact that, so what did I show? I showed that this, right, no, I showed that this one is equal to this one. I showed that this rectangle is equal to this square. But I still need to show this rectangle is equal to this square. But, you know, there's no real distinguishing any of this picture. So I could have just drawn this triangle, right? And this triangle, shown that they're congruent, therefore their areas are equal. And then 2 times the area of this triangle, right, is this rectangle. And then 2 times the area of this triangle is this square. And then since the two areas of the triangles are equal, the area of the square must equal the area of the rectangle, which is the exact argument I just made. And I could have done the same thing. So what we say is by a symmetric argument, we could show, okay, that rectangle BMLD is equal to ABFG, the square. Then once I've shown that, I'm done, because now I can say, right, clearly from this original statement, right, this is what we need to show, right? And then I start by making this initial statement. So this initial statement, MCEL, I just showed, is equal to ACKH. So in this equation, when I have B, C, E, D is equal to MCEL, obviously this rectangle plus this rectangle is the whole square. So then I could take out MCEL, sorry, the area of that rectangle is equal to this square. So I could just write it, that's square area, plus, and then again, since this BMLD I just showed by a symmetric argument is equal to ABFG, I could write plus ABFG. And now I've shown what was desired to be shown, because I just said we need to show this here, right? This is the statement written out nicely for this general right triangle. This was any right triangle, and this argument will apply to all right triangles. So I showed this final result, and now I'm done.